In today's lecture, we will deal with sintering powders. So you created a shape and now you want to develop bonds between the particles and densify them. And so here you can see, for instance, the formation of this region called the neck based on atomic transport from this particle surface to this particle surface. You can also see the spore region, and over a period of time you can see that spore region will form a different shape. It's more rounded and smaller than the ones over here, and the growth of this neck region is a good characteristic of the formation of the bonds and other properties that allow us to tell how well we have sintered something and how can we control it. So the issues to address are measurements. That is, how can we tell how far the sintering has progressed and how much is left to go? Then we'll deal with the mechanism of solid state sintering, where the particles are all well below the melting point of the material. We'll observe some of the microstructure changes and the grain growth that occurs during sintering. And if you're using mixed powders, what happens to the microstructure, what happens to the homogenization, the opportunities for new mechanisms such as the formation of the liquid phase. Right? And so that leads us into sintering technologies and process variables that need to be taken into account along with the material variables to understand and control sintering. So sintering is basically a thermal treatment during which bonds are formed by atomic transport. Bonding leads to improvement in strength and other properties. The mass transport also leads to densification and changes in the pore structure. So the phenomena to study sintering and follow its progress include the bonding of the particles when they're heated. So the presence of these bonds allows a loss in the surface area of the particles. The bonds grow in regions called the necks, and it is accompanied by a dimensional change based on the bulk diffusion of atoms. Particle bonding results in property improvements. If you have mixtures of particles such as iron and nickel, you can have chemical homogenization. You can have grain growth, and so you'll have a coarsening in the microstructure. So that's a time and temperature related phenomenon, just like sintering is. And so they go hand in hand. And so how to control that? Right? Because all these processes are irreversible. Unlike the case in mixing, where if you had a poorly mixed material, you could throw it back into the mixer, or if there are some defective parts after injection molding, for instance, you can regrind the material and reuse that with some of the virgin feedstock. You cannot do that with sintering. After sintering, you're going to be stuck with defective parts. And so understanding the many processing parameters that help you control sintering is important to make sure that you have high yields from the end of the sintering process. Let's take a look at these gold wires, a cross section of which can be seen over here. At 1000 degrees centigrade, these two microstructures are both same, and they've been heated for about 10 hours. And so these are relatively large wires, and you can see the formation of these kinds of bonds between the wires, right? And you can see these kinds of pore shapes. As you move from 10 hours to 24 hours, you begin to see that there is a grain coarsening, and now you begin to see some spherical pores occurring from coalescing of this region over here, for instance. Right? When this is continued for about 96 hours, you can see even more coarsening that occurs, accompanied by densification. So the pores are becoming fewer and they're becoming smaller as well, right? As you can see over here. In this example, you can see a couple of different steel compositions that have very different pore structures. Here there are very tiny pores distributed around the particles. Here are coarser pores. And typically this microstructure on the right tends to have higher strength than the microstructure on the left, where there are all these tiny pores surrounding individual particles. In terms of the sintering process overall, you have two general classes. One is you apply an external pressure, or you don't apply an external pressure. So pressureless and pressure resisted sintering. In the pressureless case, you can have sintering occurring by solid state diffusion or diffusion in the presence of a liquid phase when you have mixed composition materials. Right, in the solid state, again, you could also have a mixed phase material, or you could have a single phase materials. So just gold wires like we saw earlier, or a mixture of iron and carbon, for instance. And in this manner, you can have activated sintering, you could have homogenization of the components, or you could have composites. When you have liquid phase, what happens is atomic diffusion through the liquid phase is a lot stronger, and so you can have a liquid that solidifies and remains there at the end of the whole process, and you have a couple of variants over there. Alternatively, there's a liquid formed initially, and then it reacts with the solid phase and forms a solid solution. Okay, these are some examples that we will see. In the pressure assisted case, it's now more analogous to forming, and so you can apply different quantities of pressure. And now, in addition to just diffusion mechanisms, as you can see in the case of pressureless sintering, you can also have mechanical deformation, so creep flow, viscous flow, plastic flow, and so on. As a result of so many different mechanisms and so many different chemistries, you can have widely different microstructures as a result of sintering. And so, without knowing anything about what these materials are, you can pretty much say that all of these contribute towards very different properties. In addition to microstructure changes and property changes, you also have dimensional changes. This is an optoelectronic package that has been injection molded. On the left, you see a green part that is as molded condition, and then after the polymer is removed during debinding and then sintering is done, you end up getting this type of a shrinkage. This is an iron nickel alloy called Kovar that is used for packaging, and you can see the dimensional changes. You can also see that these dimensional changes are held nicely over 3 dimensions, over a lot of different features. When dealing with different kinds of sintered materials, the earliest were inexpensive materials such as clay and silica. You could make bricks. Then it moved on to the industrial age where you could have aluminum oxide. The current growth and opportunities in sintered materials often encompass very difficult to sinter materials such as silicon carbide, silicon nitride, aluminum nitride, and so a lot of value is generated from being able to process these materials. So the opportunities are from going from poor precision materials such as bricks in the historic times to the point where you can get high precision, high complex parts with good structural properties. They can perform under demanding conditions such as high temperature. They're fully dense, and you can create high value applications